So what we want to talk about today is these transformations. I want to go back and discuss transformations again. And I want to jump back and forth between a couple different GeoGebra things that I've created for you and this board over here, and just draw some rules up over here and then see if we can recognize the relationship between the rule and what that rule is actually doing to the graph. That graph paper, I don't know how much we're going to do one graph today, but I don't know how much we're going to get into, like actually graphing specific functions, like an x squared or x cubed or something like that, or a root function. I'm just going to start off with some generic function, okay? And that's what we're going to graph today. But keep that graph paper. Use it as you deem necessary. I was kind of a person that I prefer to have the graph in my notes, so I would just draw it in my notes. Obviously, like maybe drawing things in your notes, not as easy as the graph paper because you got to make your own intervals and that kind of stuff. But there are restrictions that graph. If we go do some stuff here in a moment with some ordered pairs that are bigger than 10, those are 10 by 10 graphs, and your graph paper has its limitations, right? I had a 20 by 20 graph for you. From negative 20 to positive 20 in both directions, but that was really small and ugly looking. Okay, so here's a 10 by 10, and hopefully maybe it addresses some of our needs, but again, I understand there's limitations to that. First thing I want to talk about is when we start introducing rules, and you're going to see this in the transformation assignment you saw on WebAssign, if you've looked at that yet, they're going to just kind of generally speaking, just talk about the function as f of x, okay? Where that function might actually be x squared, it might be x cubed, it might be logarithm of x or natural log of x, it might be 1 over x, okay? When they say f of x, they're thinking, or they're making the connection with you that it could be any one of these parent functions that we kind of talked about the last couple lectures, okay? We've seen that chart before, right? Okay, so f of x could be any one of those things, okay? And really this is just kind of a small snapshot of the different functions. We would have x to the 4th, the 5th, the 6th, and so forth. We got the 4th root, 5th root, 6th root. We got a to the x. So that's 2 to the x, 3 to the x, 4 to the x, e to the x, pi to the x, any number you want a to be. So there's an infinite number of functions there. Same thing with the logarithm, base a of x, reciprocal function. Okay, your numerator could be 1, could be 2, could be 3, could be anything. So there's a lot of different functions here. And then we start to see down here we get our trigonometric functions, which we'll talk about in trigonometry, and those are only 3 of the 6, maybe 3 of the 12 that we'll talk about. But we can do all the transformations that we're going to talk about with any one of those and any of the ones that are maybe missing from that worksheet that we'll talk about throughout the course. Does that kind of make sense? So they just generally condense them all and say, just call it f of x. And it doesn't really matter which one you're viewing now. Okay? So if that doesn't matter, let's just create just a generic function. Okay? If I start with that generic function, it does pass the vertical line test, right? Okay, and really to do the operations that we're doing, it probably doesn't even need to pass the vertical line test. But we're gonna, because we're using function notation, probably makes sense to make sure our graph is a function. So I'm going to graph these points. All right, it's not a smooth curve, right? Okay, it's kind of jagged, rigid. Maybe it's behind the scenes, maybe it's a bunch of piecewise functions. Does that make sense? Okay, maybe 5 different sections of different lines that we've put together to create that function. The normal function, they look at all those piecewise functions, except for things that were linear, they were all smooth curves, right? There's no corners, because what happens in calculus when we have corners, we don't have the ability to do differentiation. Okay, and that's a huge part of calculus. So we want our things to be smooth, but we can still learn the process and the understanding of what's happening when we start applying transformations to the function. We can look at what happens to the y values, what happens to the x values, and then see if there's a connection. Okay? So the first thing I want to talk about is what happens when I just start with f of x, and I add or subtract some quantity from f of x. Remember, with f of x, okay, we are saying that y equals f of x. So your y values are your f of x values. Does that make sense? Okay? So the f of x rule, whatever that function is what is creating your y values. Okay? Well, if I read this that way then, doesn't this say whatever your y value is, add to it or subtract to it some constant? That make sense? So if I just have, for a specific example, that's f of x over there. Let's say I have f of x plus 3. Okay? F of x plus 3. What is that going to do to every one of the y values that is over here? Add 3. Does it do anything to the x values? No, there's no rule there telling me to do anything to the x values. So negative 5, comma 1, I'm going to add 3 to the y value. Gives you that point there. Negative 2, 0, I'm going to add 3 to the y value. Gives you that point there. 0, negative 2 goes to 0, 1. 1, 4 goes to 1, 7. 3, 3 goes to 3, 6. And 8, 3 goes to 8, 6. Okay, now, move over a little bit, move out so I can connect these. And the idea is if I can move those kind of corners for the function are kind of critical points, right? When we graph a smooth curve, our critical points are going to be like vertices. Like for a quadratic, it'd be the vertex, be the maximum or minimum, right? For cubics, it'd be those local maximum minimums. Maybe x-intercepts, maybe y-intercepts. Those are some critical points. If we can move those correctly, so I move, A to G, and whatever that, I'm assuming that's probably point B, move that to H. If I move those two correctly, did I move everything in between correctly? Okay? So that's kind of the idea. If we can move a series of critical points correctly, then the points in between will also move accordingly. Okay? And hopefully you recognize and view that as if I take the black curve, or not curve, but black function, and I slide it 3 units up, it becomes the red one, right? Okay? So plus or minus c, go plussing c is going to move it up, subtracting c is going to move it down, right? Okay? So this is what we call a vertical shift. Okay? A lot of textbooks use the word shift. It's not really a math word. Translation is the math word for shifting up and down, or left and right. So vertical translation, vertical shift, it's adding something to your y value. Okay. What I've done, and I haven't found the best place to kind of put these because they're kind of big in regards to their kind of loading process if I put them on my website all at once. But I've created kind of individual GeoGebras that deal with just one transformation at a time. So I've got where's the vertical shift? There we go. But it allows you to type in any function into this box here that you want, okay? And then add some constant b to the end of it, okay? So I'm going to say, x squared plus b, and then I'm going to slide that b. You can see then how that adjusts and creates the actual function that's being graphed. So I have x, does that thing x squared plus 2 look like x squared? Just every point has been moved up 2, right? Okay. So the idea here is if I had just x squared, okay, every single point on that. So we've got a couple points. We've got 0, 0 that we've committed to memory. We've got 1, 1. We've got 2, 4. We've got, negative 1, 1, we've got -2, 4. We've committed all those points to memory, right? The idea is every one of those points then gets moved up 3 units, moved up 3 units, moved up 3 units, moved up 3 units. So if I move those parent function points, and that's why I said we need to memorize, maybe not memorize, but understand a series of ordered pairs for all our parent functions. And if we know those, and we add 3 to them, we can move every one of them up 3 units. We can add 3 to every y value, right? And that's going to produce, then that green curve is what we want. Okay. But I think what's convenient about this is it shows similar relationships regardless of the function. So I can come in here, and I'm giving you some rules down here to kind of type this in using the correct syntax for GeoGebra. But if I put x cubed, okay, and now if I put +1, you just see that it just took that function and moved everything up 1 unit, right? +2, +3, -1, -2, that kind of stuff moves it down. But we can do the same thing if I want to go square root. Okay, so then change my b value. You see how that looks algebraically at radical x +2, it moves it up 2. Radical x -1 moves it down 2. Okay. Maybe some functions that you guys aren't familiar with. You should know what the natural log is, okay, from Algebra 2, but we'll have a whole chapter where we basically do exactly what you did with logarithms last year. Some of you might not like that, okay, but I think maybe some of the things that, the way I do it, the way I teach it, I think it helps people understand what they actually are. They're really not that hard. But if I just type in ln of x, okay, ln of x is that curve right there, okay. Well, if I start adding values to the end of it, okay, look at what it does to the y values. Okay, I had a point 1, 0 there. Add 1 to it, the y value goes to 1. Or the point now is 1, 1. Add 1 more, it goes to 1, 2. So it's just moving that function up and down, right? So it does not matter what type of function you plug in. If you're going to add something to the end of it, 1/x plus b, okay? 1/x looks like that there. Add 1 to it, takes the whole thing, moves it up 1. Okay? Moves the whole thing up 2. Does that kind of make sense? Okay? So that is what a vertical translation looks like. And you can then see how that impacts your parent function and then creates algebraically what a bunch of other functions look like. And that's kind of the goal, is that, you know, eventually if I give you some long function that has a bunch of different components to it, you can kind of piece together one at a time. Well, this component does this to the function. This component maybe stretches it. This component moves it left. This component reflects over the x-axis. And then you can get your graph pretty quickly. Does that kind of make sense? All right. And maybe not even just graph it, but just have a visual image of what you're dealing with. Okay. Now, a lot of times when we talk about, you know, we've added to the y value and seen how that affects the graph vertically, right? Well, let's add something to the x value then and see how that impacts things. So this is impacting a y coordinate. To impact an x coordinate, we're going to do this. We're going to take f of x, but instead of adding c to the end of it, we're going to add c on the inside. We're going to add c to x. And really what's going on here, when we write that notation, we're saying that whatever your function is, maybe your function is like the square root of x, okay? We are going to, you know, take a number. Maybe I give you a number like, let's say we have the square. So this is what this is going to look like. The function square root of x is going to look like that, right? Okay. But now we're doing maybe that. Okay. So we're subtracting the x, a value from the x before we take the square root, right? Okay. So what happens if I give you a number like 4? Normally, if it was just square root, your output would be 2, right? Okay. And if it was square root of x and a -3 out here, okay, and I gave you 4, your output would be 2. Okay, your y value would be 2, but then you remove 3 from that y value, right? Okay. Well, now what we're going to do is we're going to remove the 3 from the x value first. So if I give you 4, remove 3 from it, you get 1, right? Now you're going to take the square root of 1. Okay? So you're subtracting something from the x value before you take and apply that dominating function. Does that make sense? Okay? And that's ultimately going to get your function to move left and right. Okay? So this becomes a horizontal translation, left and right. Okay? Now, if it's plus c, it actually moves left. If it's minus c, it moves right. And we've talked about this before when we dealt with circles. If I had like x plus 3 squared plus y minus 4 squared is equal to like 81. Okay, a normal circle, I guess the initial circle we talk about is always centered at 0, 0. That's going to move it left 3, right? And that's going to move it up 4, right? Okay, and that's kind of counterintuitive to what we would normally think with pluses and minuses. But we are going to impact the x's in this case. Okay, so adding c moves them left and right. C could be positive, C could be negative. So if I'm adding a positive number, it moves it left. If I'm adding a negative number, it moves it right. So let's say that we want to stick with this same function here, but I want to rewrite it as f of x. Let's go plus 3 now. Somebody put something like on my board. My markers aren't working very well. Throw the markers away. That should fix it, right? So we're gonna move it to the left 3. So every x value now becomes 3 less, right? So I'm gonna get negative 8. Did the y value change at all? Nope. So negative 8, 1. Negative 2. Negative 3. Okay. I'm sorry. Negative 5, 0. Remove 3 from the x, right? So negative 5, y value stays the same, 0. Negative 3, comma, negative 2, y value stays the same. Negative 2, comma, 4, y value stays the same. 0, 3, and then 5, 3. Okay? So now connecting those, okay? If we look at that, does that red curve look like the black one just shifted 3 units to the left, right? Okay. And again, I'll post this for you at some point, but you can mess around with it. I like these because it allows you to just focus on one thing at a time. Okay. So we can change the function that we want to. Right now I've got x squared in there as the parent function, but if I add 1 to it, we see what it does. It moves it to every point goes 1 unit to the left, right? Okay. I don't know if I can trace what happens. Yeah, kind of shows you those successive functions, right? Okay, where they were previous to where they're developed now. Okay, so that's kind of ugly. You get a lot of them in there. But you can change this function. If I want to go x cubed, okay, there's my initial function. Move it to the right. Sorry, add 1 moves it to the left. Add 2 moves it to the left further. It keeps going, right? But you see then algebraically that's a plus sign that's moving left. If it's a minus sign, it's going to move it to the right, correct? I think it's easier maybe sometimes to recognize with the square root function what we're doing here. Okay, because now normally when we had the square root function, we were adding things to the outside, but now you see that you're adding stuff underneath the root function, and it moves it to the left, right? And we talked last week about, or earlier this week, I guess, about how that should make sense, because what does that x plus 1, what kind of number does that have to be? It has to be positive, right? Or it has to be 0 or positive, right? So I set that greater than or equal to 0, solve, and it says x has to be greater than negative 1, and that's what we're seeing here along this x-axis, is that our domain values are greater than or equal to negative 1. And then if I keep changing that, it moves it further along that x-axis in that direction. X minus 2, 3, 4 moves it in the right direction. Okay. Normally, the biggest issue I see with people dealing with translations, because these are really the easiest ones to deal with of the transformations we do. The biggest mistake I see people making is when it's a left and right. They want to, when it's minus 3, they want to move it to the left 3. When it's plus 3, they want to move it right 3. Okay, but it's opposite that. Okay, so you always got to kind of force yourself to think. Horizontal shifts are kind of counterintuitive to what we would think when we see it algebraically. The next transformation is, let's talk about what happens when we just multiply f of x by some constant, some coefficient out here in front of f of x. So we might start with like something like x squared, we might start with something x cubed, square root of x, whatever. Maybe we're going to start with the black function over here that provides some rule that provides us all those ordered pairs there. But now let's say I want to take that f of x and I want to make it 2 f of x. Okay, so we're looking at something that not like that. Well, we'll go 2 f of x. Now, we'll think about what that means. Okay, f of x, come back to this, f of x was your y values, right? Well, 2 f of x then is going to do, it's going to multiply your y values by that factor of 2. Does that make sense? Okay. So now, looking at all these ordered pairs, okay, if I take a and multiply its y value by 2, it's going to go negative 5, 2, right? Okay. Negative 2, 0 multiplied by 2 just stays at 0. When we get 0, negative 4, I'll get 1, 8, 6, 3, or sorry, 3, 6, and 8, 6, right? And now if I connect those, it's still kind of the same type of picture, but you see how it's gotten pulled vertically, okay? Your y values have been stretched, okay? Anything on the x-axis stays on the x-axis because your y value is 0. Multiplied by anything you see is 0. But every other point gets stretched vertically by that value of c, okay? So, if c is greater than 1, okay, we have what we call a vertical stretch. Okay? If c is greater than 1, we have a vertical stretch. Okay? But what happens when c is not greater than 1? And that's what we got to talk about.